hear me? Okay. Good afternoon. Welcome to the colloquium. My name is Hiroshi Oguri. I was the chair of the board of this center until last summer, and I am an honorary trustee now. It's my great pleasure to introduce today's speaker, Alex Maloney, from Syracuse University. Alex received a bachelor's degree from Stanford and his PhD from Harvard under the guidance of Andy Strominger. He was a postdoctoral fellow at SLAC and the Institute for Advanced Study in Princeton before becoming an assistant professor at McGill University. He was at McGill for 17 years, during which time he became a James McGill Professor and Sir Williams MacDonald Chair in Physics. Last year, he moved to Syracuse, where he's the Kathy and Stan Walters Professor of Quantum Science and Director of the Institute for Quantum Information Science. He was elected a member of this center last summer and has been contributing to the running of the center also. He has received many awards and honors. Among them is the CAP-CRM Prize in Theoretical and Mathematical Physics, which is awarded annually to one Canadian physicist or mathematician. This colloquium, I would also like to point out that he received McGill University's John David Jackson Award for Excellence in Teaching, so we can expect an excellent presentation today.
You can expect a level of
pedagogy of classical electromagnetic
with Jackson's textbook, right? So,
which I regard as a torture tool for graduate students. Alex told me that he's happy to answer questions during the talk. However, I would like to point out that this colloquium is intended for participants of the other two workshops to encourage cross-workshop conversation. This is to introduce about his workshop to the other two workshops. Therefore, I will actively discourage questions from participants of the Bootstrap, Holography, and Swampland workshop. We can make an exception to this rule only if you genuinely believe that your question will add value to the audience from the other two workshops, not just for your own satisfaction. The title of this talk, his talk is Wormhole, a Black Hole, and Conformal Bootstrap. Please.
well, thank you, Hiroshi, for that very kind introduction. Thank you. Can you guys hear me okay? I have this sort of Britney Spears thing. Okay. You can hear me? Great. Good. So, thank you all for coming to this mandatory colloquium. The good news, I've kept it to a quick 2 hours. The test at the end will be multiple choice, so you really have nothing to worry about. No, again, we're just here to have fun. So please, I also, as Hiroshi said, I want to encourage everyone to interrupt and ask questions at any time. I have no particular agenda. Happy to be distracted and answer any questions that you guys might have. But I'd like to begin just with a very, very general overview of the kinds of questions that I'm going to try to talk about today. So the two pillars of modern physics are quantum mechanics and the standard model of particle physics, as well as Einstein's theory of general relativity, which is a theory of gravity. Both of these theories, as far as we can tell, are correct in their individual regimes of validity. But of course, as you're probably aware, they appear to be fundamentally incompatible with one another. And there are many ways of thinking about this incompatibility, but I think one of the easiest ways of understanding why these two theories are in tension with one another is thinking about the role that time plays in these theories. So for example, in quantum mechanics, time evolution is unitary. The number of degrees of freedom does not change in time, or you might say a little more poetically, information is neither created nor destroyed in quantum mechanics. On the other hand, in general relativity, the geometry of space-time is dynamical. In particular, the geometry of time is dynamical. Space can be created or destroyed. example, we're in an expanding universe, which means there's a sense in which space is continually being created. This seems to be really in tension with the idea that the number of degrees of freedom cannot change in time in a quantum mechanical theory. So that's led many people over many years to speculate whether the basic laws of quantum mechanics even apply in theories of gravity. That is to say, is the set of states in a theory of gravity described by a Hilbert space in the usual way? Is time evolution described by a unitary operator generated by a Hamiltonian the conventional way in a quantum mechanical system? These are the kinds of questions that we want to address when you're thinking about quantum mechanics and gravity at the same time. So the question then is, how can we study quantum gravity? And I think one of the most straightforward approaches that we could try and take would be to think about gravity from a path integral point of view. So I remind you that Feynman taught us, really going back to Dirac, but mostly Feynman taught us that quantum mechanical systems can be thought of as an integral over the space of possible configurations weighted by the exponential of the action. So in the case of gravity, general relativity tells us that gravity is a theory of dynamical metrics. I've denoted G here. And so you might think that if you want to study quantum gravity, you could do something like integrate over a set of metrics weighted by an appropriate action. In this case, if we're talking about quantum general relativity, action would be the Einstein-Hilbert action for general relativity. Don't remember what that is, that's okay. I might write it down later if you're interested. But basically, what one might try and do is perform a path integral computation in order to treat general relativity in a quantum mechanical way, just as you would any other quantum mechanical system. This is what sometimes would be known as a sum over geometries, because the configurations that describe space-time in general relativity geometries. But unfortunately, and this has been known for a very long time, when you try and treat general relativity as a quantum mechanical theory in this way, usually it makes no sense, okay? And indeed, what one finds is that additional degrees of freedom seem to be needed, not just a metric, but other stuff as well, in order to come up with a full theory of quantum gravity consistent with the rules of quantum mechanics. What I want to do today is think about this in a little bit more detail. Think about this treatment of quantum gravity as a sum over geometries and see exactly how it fails. The way that it fails is going to be very interesting. It's going to teach us something about the nature of quantum gravity. And really, get to the title of my talk. It turns out that there are a particular kind of geometries known as wormholes. They're really the smoking gun for the failure of this approach to quantum gravity. Okay. Now, wormholes, you know, we see them in science fiction movies. We hear about them. They're kind of interesting, kind of crazy. I have tenure, so I'm allowed to talk about crazy things like wormholes. But I want to be clear exactly what I'm talking about when we talk about wormholes. So, you know, if you read about wormholes in science fiction, kind of wormholes that you might read about or hear about, the kinds of wormholes that Jodie Foster jumps through in a movie where it allows her to go from one region of space-time to another region of space-time very quickly, okay? These are not the kind of wormholes that I'm talking about today. Those wormholes are what we usually call traversable wormholes, wormholes you could actually travel through. And those are space-time geometries, okay? They're solutions of general relativity, for example, that connect very distant points in space-time that allow you to move between them very quickly, okay? Instead, when I talk about wormholes today, I'm talking about something different, something a little more confusing. It's a little bit more like the Matthew McConaughey wormhole as opposed to the Jodie Foster wormhole, right? It's something weird and quantum-y, and you know, it's a little more confusing. But really the kinds, so a few people laughed. Okay, so I'm getting a sense that maybe I'm
the problem is
jokes are a little
Jodie
stale.
Foster didn't go anywhere, and Matthew McConaughey actually went through a wormhole. So your metaphor was completely wrong.
All right. Okay.
See,
Thank you.
To laugh.
Thank you, Paul, for your trenchant observations as always. Okay, good. So the sorts of wormholes that I'll be discussing today are what are known as Euclidean wormholes. Okay, so these are geometries. Okay, because they're solutions of gravity. They're spatial geometries. They connect distant points in space, not distant points in space-time. Okay? And because of that, we call them Euclidean. Because their solution, so if you remember in, special relativity, the geometry of space-time has signature minus plus plus plus. That means there's one time direction and three spatial directions. These kind of wormholes are called Euclidean wormholes because they're purely spatial, okay? And their interpretation is a little subtle, it's a little confusing, it's a little different. And so before I dive into any details, any technicalities, I just want to tell you a little bit about their interpretation, okay? And this is going to involve the most difficult computation that I'm going to do during this talk, which is a Gaussian integral, okay? So hopefully we're up for it. We'll take a deep breath. Okay, good. So how do we think about these wormholes, and what might they teach us about quantum gravity, about nature, when we think about quantum gravity? So I want to start by thinking about the dynamics of some field theory, okay? Field theory could be your favorite field theory. It could be electromagnetism, could be quantum electrodynamics, could be something like that, okay? That means that we're studying a theory for a field, phi. Could be the electromagnetic field, if you like. And then the dynamics of the theory is governed by some Lagrangian. Okay, so what does that mean? That means that if you want to study the quantum mechanics of this field, say the electromagnetic field or QED or something like that, you would integrate over the possible field configurations weighted by this action, okay, which is the integral of this Lagrangian. Okay, so this is the sort of thing that you might think about if you were studying quantum electromagnetism or electrodynamics or something like that. Now, let's ask ourselves what might happen if we add wormholes to this theory. So what is a wormhole? Wormhole is a configuration, a geometry, that connects distant points in space, okay? I want you to look at this wormhole here, and I want you to think about its two endpoints, okay? We've got an endpoint here that we could call X, and an endpoint here that we could call Y. The job in life of a wormhole is to introduce some sort of coupling between those two endpoints, okay? So what does that mean? That means that there's some operator or some observable in this field theory that's going to get some sort of what we would call a bilocal coupling, okay? So if you like, what you could take, if this is quantum electrodynamics, this O could be the operator that creates an electron or destroys an electron. And then you would need to, if you have a wormhole in the theory, you would need to add this coupling to this action. And by adding the coupling to this action, what you're saying is that due to this wormhole, you can have an electron that disappears from this point and then reappears over here. So this is the sort of effect that a wormhole might have on some sort of theory like electrodynamics.
What does the I stand for?
Oh, so the I is going to label different sorts of operators or the different sorts of couplings that could be induced by this wormhole. Okay?
And this is basically a two-point correlator.
This is a two-point correlator. It's a two-point correlator, but there's something interesting happening. Okay? Because the point of a wormhole, and what I mean by a wormhole, is that the amplitude for this to occur is going to be independent of the separation between these 2 points. And really what we're going to need to do, thanks for that question then, is integrate for all possible wormholes, by which I mean all possible endpoints of the wormhole, okay? And so the effect of adding this wormhole to quantum electrodynamics, for example, would be to take this original Lagrangian, and we augment it by this bilocal interaction, where we integrate over X and Y the possible endpoints of the wormhole. And the key point is that when I do that, I get something that doesn't depend on the spatial separation between these guys. It doesn't depend on the distance between X and Y. So you can stare at this for a second, and if you stare at it, you'll quickly realize that there's a different way of writing this thing. okay, which involves Gaussian integral. Okay? So in particular, what I could do is I could introduce a new parameter. This is just a number that I'll call alpha. And then I could take this and observe that if I just take my original theory, but augmented by the addition of a new term, alpha I OI, and I integrate over alpha I with an e to the minus alpha I squared, okay? If I did that Gaussian integral, it would just get this thing that I've seen up here. Okay? So what does that mean? That means that if I have a theory, say quantum electrodynamics, I add in the effect of wormholes that can connect all possible points, all possible pairs of points. Okay? That's indistinguishable from a theory where I take my original quantum electrodynamics and I deform it by turning on an additional coupling. Okay? But this coupling is a random variable. So what does this mean? This means that in a theory of gravity that has wormholes, low energy physics is one where all of the coupling constants are random variables. The fact that I had these bilocal interactions means that it's a theory where the coupling constants are Gaussian random variables. And I left out a bunch of details here, but for example, the width of that Gaussian distribution of couplings will depend on the properties of these wormholes. And this is the basic idea. And it's kind of a crazy idea, but in my defense, I didn't come up with this idea. This idea really originates with Sidney Coleman back in the 80s, with many other people, sort of most notably Giddings and Strominger at around the same time. The idea really is pretty interesting. The idea is that if you have these wormholes, that the effect is indistinguishable from all of the fundamental constants of nature being random variables rather than having fixed values. Please, question.
So you call the others, the Jodie Foster wormhole, the traversable one.
Yes.
So why is this nomenclature? Why is this not traversable? Because this is also making stuff disappear and appear. Right?
So the reason why this is Euclidean wormhole is that if you remember the path integral formulation of quantum mechanics that you probably learned, in your quantum class, you had a factor of I sitting here. And you were computing a unitary time evolution operator. I didn't tell you, but I left out that factor of I, and so this is a real number. Okay? And because of that, I could really interpret these as Gaussian integrals. Okay, because when you have e to the minus something, so you're doing Gaussian integrals. If I'd stuck those factors of I there, it would have been much more confusing, and I wouldn't really have Gaussian integrals. I'd have something like a Fourier transform or something like that, Legendre transform. Now there are Lorentzian interpretations of these Euclidean wormholes that I might get to if people are interested and people have time, but it's a little more complicated than just what Jodie Foster did. It's what Matthew McConaughey did, which is something weird and confusing. I don't quite know what was going on in that movie. Okay, good, great. So any other questions? Now, if you're like a particle physicist, the idea that the coupling constants of nature are not fixed but are random variables is very disturbing. If you're a condensed matter physicist or a materials physics person, this is great because this is what you do all the time when you study disordered systems. In fact, in the language of condensed matter physics, what this means is that theory with wormholes is a theory with what we call quenched disorder, okay? Where the coupling constants are random variables. And this is a very common model that we use in condensed matter physics. Typically, it's used when you're studying a material whose coupling constants are very complicated. Like if you're studying some interacting spin system, very, very complicated interactions, you might throw up your hands and say, well, those interactions are so complicated that I might as well just treat them as random variables. Right? And in many cases, this is an astonishingly good approximation to the theory that you're trying to study. And indeed, the upshot of my talk at the end would be that general relativity, in a sense, should be thought of as a theory with quenched disorder. The same way that the theory of a spin glass, where you treat the interaction terms in a Hamiltonian as random variables is a theory with quenched disorder. Yes, please.
Very naive question. This actually makes one wonder if you can make a condensed matter system with quenched disorder that has a Lagrangian like the modified one you have there, that you can in some sense make a wormhole using condensed matter. Is that a
People have certainly talked a lot about this. People don't usually talk about QED, for example. That's a very complicated theory. People do talk about, for example, the SYK model, the Sachdev-Kitaev model, which is a theory of interacting fermions with a disordered coupling. Indeed, there have been claims that people have been able to engineer SYK systems with complicated enough couplings. You might want to think about it as a wormhole in a sense like this. I think there's some discussion about how seriously to take those experimental claims, but we can leave that to a different discussion. Thanks. Great. Any other questions? Okay. So this is all pretty weird. What does it all mean? Okay. Is nature a disorder averaged theory? Okay. What is quantum general relativity, and how would it be related to a full theory of quantum gravity? And what I'm going to claim today is that I'll kind of pretty much answer these questions, but in a very simple theory of gravity. And the way that I'll answer them is using what's known as the ADS-CFT correspondence, and one of the most powerful tools that we have to study it, which is known as the conformal bootstrap.
Question.
Please.
When I think of a disorder average, usually I imagine, say, fixed, in your case, coupling constant, and then I work out the dynamics, and this dynamics will not have the field somehow magically being coupled between very different places.
Correct.
And only after I do the whole averaging, this will happen. But my understanding was the wormhole should couple very different places.
Okay. So a Jodie-Foster wormhole really does lead to couplings between radically different things. These Euclidean wormholes are something different. And as I tried to argue here, maybe too sketchily, is that the effect of these Euclidean wormholes is exactly that the coupling constants of your low energy effective theory would be effectively random variables. And there's an example that if we have time, I'll show in detail where this is completely precise. This is exactly what happens. Yeah.
You keep referencing these people. I have no idea who you're talking
Jodie Foster. Okay.
The most guy?
Jodie Foster. Oh my God. Where are you? what rock have you been living? No, I'm sorry. There's a famous movie called Contact where Jodie Foster jumps through a wormhole. And there's another famous movie called Inception where Matthew McConaughey maybe, what's it called? No, what's it called? Interstellar. Sorry. Okay. There's a movie called Interstellar where Matthew McConaughey maybe kind of does something weird in quantum-y that's maybe a wormhole. So I'm trying to make a joke. But based on this, maybe I should stop making that joke. Okay. Good. Right.
Leonardo was Inception. I'm surprised you didn't say Leonardo DiCaprio.
Yes, to the best of my knowledge, no wormholes were harmed in that movie. Okay, good. So what's my plan? I'm going to tell you some basics of the ADS-CFT correspondence, a little bit about the conformal bootstrap, what it has to do with black holes and wormholes, and then I'll end with a little bit of rampant speculation. Okay. So like any good talk about quantum gravity, I have to start by talking about black holes. And bear with me for a minute. This will make, we'll come back and you'll see why this is relevant in a minute. What is a black hole? A black hole is an object that is so dense that nothing, not even light, can escape from behind the event horizon. But Hawking taught us that actually, according to the rules of quantum mechanics, black holes will decay. They will emit radiation. And that radiation will have a characteristic temperature that's given by this formula here. And in particular, it's a quantum mechanical effect. So this temperature involves an h bar. So what Hawking really taught us is that black holes have a temperature. And therefore, the first law of thermodynamics, black holes have an energy, which they have to because they have mass. They have a temperature, because that's what Hawking taught us. And they must have an entropy. And that entropy is determined by the first law of thermodynamics. TE is TdS. Okay? So if you took that temperature that I gave you on the last slide and you integrated this first law of thermodynamics, you would get an answer for the entropy. And that answer has a particularly surprising form. The entropy of the black hole is proportional to the area of the event horizon of a black hole evaluated in Planck units. So I've divided by L Planck squared there. Okay. And so this observation was really the starting point for the idea that quantum gravity is holographic in some sense, because the entropy of a black hole is proportional to its area. Now, how could we study this in a little bit more detail? Well, Hawking taught us that black holes emit radiation. Okay, they emit radiation, therefore they're unstable. So the first thing that you would want to do if you wanted to try and make some of these ideas more precise is you would want to make the black hole stable some way. Okay? So one easy way of doing that is taking this black hole that's emitting radiation and putting it in a box. Okay? So here I've drawn a black hole and I've drawn a circular box or a spherical box around it. I'm imagining that I'm putting reflecting boundary conditions on this box. Okay, so the walls of the box are a mirror. So what does that mean? That means that when this black hole emits a Hawking quanta, some Hawking radiation, it'll just get reflected back in. So when you do that, you'll discover that it's possible to have black holes that are stable because they can be in equilibrium with their own Hawking radiation. In particular, what that means is that if I take gravity in a box, and the typical high energy state is going to be a black hole. Right? Because if I have a box of finite size, I start dumping energy into it, and eventually, if you take enough energy within a finite size, it's going to collapse into a black hole. And if my box has reflecting boundary conditions, if it's a bunch of mirrors, and that black hole can be stable, because it can be in equilibrium with its own Hawking radiation. So what that means is that if you want to study quantum gravity precisely, you don't want to do it in an infinite space like the one we live in. You want to do it in a box. And in particular here, I'm imagining studying a black hole in a box whose size is L, some characteristic size. Now, if we're doing gravity, building a box out of mirrors is hard. Okay? So instead what we do is we build a box out of geometry. And the kind of geometry that is the simplest box that we can use to study gravity is a geometry that's known as anti-de Sitter space. Now, geometry of anti-de Sitter space is pretty simple. If you wanted, I could go ahead and write down the metric on anti-de Sitter space in your favorite coordinate system or something like that. But actually, I don't need to, because geometry of anti-de Sitter space is simple enough. Like it's entirely captured in this picture by Escher. Okay? So what is the rule to understand the geometry of anti-de Sitter space? Well, this picture, anti-de Sitter space is a disk, okay? It's contained in that circle. No, that's the circle here, okay? This is the same as that circle. The rule that you need to remember to understand the geometry of anti-de Sitter space is that each one of these little fish is exactly the same size. Even though they're drawn as if they have different size, because that's the kind of thing that Escher was into, the rule for the geometry of anti-de Sitter space is that each fish here has exactly the same size. You can see there's an infinite number of fish here. Okay? But if you stare at this picture, you'll see that actually there's an interesting symmetry of this geometry, which is that as each one of these fishes steps out towards the boundary of this disk, they rescale in size by a constant factor, right? Like this fish is twice the size of this fish, which is twice the size of that fish, and so on and so forth. Okay. So this is a kind of symmetry where all the fishes rescale by a constant amount as you get out towards the boundary. And a symmetry where things rescale by a constant factor is known as a conformal symmetry. And it's that observation which is really behind this ADS-CFT correspondence, which is the statement that a theory of gravity in anti-de Sitter space is the equivalent of what's known as a conformal field theory that lives on the boundary of the anti-de Sitter space. So let me explain those words in a little bit more detail. What that means is that a theory of gravity that lives in this disk here, remember this is where we're studying gravity in our box, so you might have a black hole in the center or something like that. A theory of gravity that lives in this disk here is the same as what's called a conformal field theory living on the boundary of that disk, which is this circle. Now, what is a conformal field theory? Okay. Well, a field theory is just a quantum mechanical theory where the observables are local operators, okay, like electromagnetism or something like that. And a conformal theory is just one that has no dimensional scale. Okay? Classical electromagnetism is an example of a conformal field theory because the photon has infinite wavelength, right? So it has no dimensional scale. Quantum electrodynamics, however, is not, because there's a scale which is the Compton wavelength of the electron. Now, there's another, so conformal field theories are all over the place, okay? Whenever, for example, you have a statistical mechanics system that has, you know, some scale invariant fixed point or something like that, that's described by a conformal field theory. Many of the most interesting quantum field theories are conformal field theories, and indeed, because conformal field theories are the endpoints of renormalization group flow, kind of the building blocks for all quantum field theories. Okay? But if you want another example of a conformal field theory to keep in your head, one of my favorite examples would be the Ising model at its critical point. So what is the Ising model? The Ising model is a theory of interacting spins, okay, with just bilocal interactions between them. And if you study the Ising model at some temperature, there'll be a typical correlation length between the spins. But as you tune to a critical temperature, that correlation length diverges. Right? It means it's a theory with no dimensional scale. Okay? And it's described by a conformal field theory. In this case, it's a simple two-dimensional conformal field theory, right? Because I have a two-dimensional grid of spins. Okay. Now, what does the ADS-CFT correspondence mean? It means that theories of gravity in anti-de Sitter space are equivalent to conformal field theories. And over the last, 30 years or so, there have been many, many examples that people have been able to understand very precisely. So here I've just written down a list. This is not all of them. This is a highly non-representative list. This is just a few of the examples where on the left-hand side here, I have examples of some theories of gravity, starting with very, very simple, most stupid theories of gravity, and ending up with very, very smart, very fancy theories of gravity. And on the other side, I have the kinds of conformal field theories that they're dual to. So again, here I have some sort of statistical mechanics, conformal field theories that are very simple. And down here, I have some very fancy conformal field theories, things like the ON model or supersymmetric Yang-Mills theory, very similar to the theories that arise in the standard model. And the most important, however, so one of the most important things on this dictionary between theories of gravity and theories of conformal field theory is that there's one dimensionless ratio that I've listed here that I've called C. What is that dimensionless ratio? Remember, we're studying gravity in a box. That box has a size L. The language of geometry, we call that the curvature radius of anti-de Sitter space, but it's really just the size of the box that our theory of gravity lives in. There's one important dimensionless ratio, which is the size of the box in Planck units. And that's a dimensionless ratio that I've listed here, and for all of these interesting theories, it's going to be large. Good. Okay. So that's the ADS-CFT correspondence. Yes, please.
How would you state 3D general relativity in the top line?
Let me get back to that, because the answer there is a little bit of a cheat, and the exact way it's a cheat will become clear at the end of, or will become either more clear or less clear by the end of this talk. Thank you. Great. Any other questions? Yeah, remind me at the end if I haven't answered that question. Good. Great. Okay, so let's talk in a little bit more detail about how we think about conformal field theories. So to begin, let me tell you what's the data that defines a conformal field theory. Well, the data is a list of operators. Remember, a field theory is a theory where the observables are local operators. So in quantum mechanics, observables are Hermitian operators. And a field theory is one where the observables are local operators. You know, there's one for every point in space-time. And so the data that defines conformal field theory is a list of operators along with a set of numbers. Okay? So there's an energy associated with each operator, okay, which in the language of a conformal field theory would be a scaling dimension. And then there's a set of coupling constants, okay, which in conformal field theory are 3-point coupling constants. Okay? So remember, if you wanted to define a quantum mechanics theory, data that defines a quantum mechanics theory is a set of energy, is a spectrum of a Hamiltonian, right? A set of energy levels. So a set of states, the energies of those states. And so that's what's really going on in that first line. So the data that defines a conformal field theory is a spectrum, an energy for each state. But then, because we're not just doing quantum mechanics, we're doing field theory, we also have a set of coupling constants. Okay? Those are these numbers Cij. So this is the data, a list of energies and coupling constants. And in general, the name of the game is to try and figure out what possible spectra and what possible coupling constants are allowed by nature. Okay. So this basic data that defines a conformal field theory is subject to lots of constraints. They're subject to things like unitarity, conformal invariance, and stuff like this. And solving those constraints is what people refer to as the Conformal Bootstrap program. Now, if you could solve the Conformal Bootstrap program, you could give a much more interesting talk than the one I'm giving today, right? Because you would be essentially solving quantum field theory. The conformal field theories are the building blocks of quantum field theory. If you could solve the Conformal Bootstrap, you would have a complete list of all possible data that define these building blocks of quantum field theories. Okay? And in particular, you know, we're used to studying quantum mechanical systems or quantum field theories in perturbative expansions. You know, you might study the harmonic oscillator or things that are close to the harmonic oscillator. But really, the name of the game of this Conformal Bootstrap program is to study in regimes where traditional perturbation theory does not apply. Okay? And there's actually been a huge amount of success there. You know, lots of progress over the last 15 years, especially. What I'm going to do is really just use a couple of little results in that, trying to make my argument today. But just to kind of get you used to the language of conformal field theory, let's think about this CFT that we discussed earlier, one that describes the Ising model at its critical point. So for the Ising model at its critical point, there are 3 interesting operators. Okay. There's this thing that I've called 1 here, otherwise known as the identity operator. That's the trivial operator that doesn't do anything. There's an operator that you might call sigma. That measures the spin at some point. Right? And then there's an operator that people call epsilon that measures the energy at some point. Okay? And it turns out that for the 2D Ising, you can actually solve that theory exactly, which means you can find all of the energies of those 3 operators, and you can find the coupling constant. Okay, there's a coupling constant sigma e. What does that mean? Roughly speaking, it means that because the Hamiltonian of the Ising model is quadratic in the spin, the energy density is determined by product of 2 spins. And you know, I won't explain to you exactly how that's solved, except that, well, people are very clever and they were able to solve it. Good. Instead, let me give you another example of something, or let me give you another example. Okay, actually, before that, let me say 1 or 2 more words about the space of conformal field theories. So what I want to do is focus on 2-dimensional conformal field theories, which will be dual to gravity in 3 dimensions. Remember, in this ADS-CFT correspondence, the CFT lives on the boundary. Okay? So it has 1 less dimension. I'm going to label these CFTs by a parameter that I'm going to call C. Okay? It's the same parameter that I showed you earlier. It's in the gravitational interpretation. That parameter C is a dimensionless number, which is a ratio of the size of the box to the Planck length. And I didn't include any factors of the speed of light or h bar or anything like that. But if you went and restored them using dimensional analysis, you would see that this dimensionless ratio C is basically 1 over h bar. So the large C limit is the thing that would correspond to semi-classical gravity, or general relativity. And of course, C has an interesting life of its own in conformal field theory land. It's basically a parameter that counts the number of degrees of freedom in the theory. So for example, if you have n free fields, the C is equal to n. And it also has important physics implications because it describes the way that this conformal field theory responds to the introduction of a scale. But the point is that, I don't know how to solve the conformal bootstrap problem. The space of conformal field theories is a weird and wild place, okay? Especially as you make the number of degrees of freedom C larger and larger. But there are nevertheless some things that we can say precisely. Okay. So for example, and this is, I think, my favorite example, it's the first one that I make all of my graduate students learn, okay, which is the following. So remember, the Ising CFT that I described to you earlier had a trivial operator that I called 1, the identity operator, the one that does nothing. And every conformal field theory has an identity operator that does 1, and that does nothing, and it's unique. And it turns out that just the existence of this unique operator, along with some version of conformal invariance, one of the consistency conditions of the theory, is enough to determine the density of states at high energy. So in particular, if the energy is large compared to that dimensional ratio, then one output of this amazing conformal bootstrap program is the density of states at high energy. But remember, conformal field theory is supposed to be dual to a theory of gravity. Right? And every high energy state is supposed to be a black hole. Right? Where's that picture? There's the picture. Every state with energy large compared to this dimensionless number should be a black hole. And it should be a black hole in equilibrium with its Hawking radiation. And indeed, if you look at the prediction from the conformal bootstrap for this density of states, you get some answer. Form is not important. I just wrote it here to convince you that I'm, not full of shit. This is the density of states at high energy. And if you go through the dictionary between if you look at a theory of gravity and anti-de Sitter space, you look at a black hole with energy E, you compute the area of its event horizon, and you find that the log of the number of states, which is an entropy according to Boltzmann, is indeed exactly the area over 4 in Planck units, exactly as Bekenstein and Hawking predicted. What does that mean? It means that the conformal bootstrap knows about black holes. Generic behavior of every conformal field theory, high energy, at least these theories that we're studying, exactly agrees with Hawking's prediction of the entropy of a black hole. Now, we go further. What about other observables? Okay. So I told you that this identity operator was universal in conformal field theories. And another thing that's universal is that if you take 1 times 1, you get 1. Okay? What does that mean? It means that there's a universal behavior for this coupling constants for these 3 identity operators. So just like in the last slide, we use this fact and we use a fancier version of conformal invariance, we learned something universal about conformal field theories. The last slide, we learned a universal thing about the density of states of a theory at high energy. Here, what you learn, it turns out, is a property of the coupling constants of the theory. In particular, what you learn is a statistical property for the variance of the coupling constants. Okay, so there's some known function here that depends on these e's and on that dimensionless parameter I called little c. I won't bother writing it down, but you get a universal prediction for the variance of the coupling constants of conformal field theory at high energy. Okay, this is a universal prediction of the conformal bootstrap. And now you might ask, just like this density of states, we obtained a universal prediction that had a gravitational answer. Okay, it was the entropy, the area of some event horizon. And it turns out that if you look at this prediction and you try and understand its gravitational interpretation, what do you get? You again find that it has a gravitational interpretation. But now, remember, this is a variance, okay? Variance is a statistical property. And so I told you at the very beginning that wormholes were related to the statistical properties, in particular, that wormhole that I showed you at the very beginning led to a Gaussian, distribution of coupling constants. Indeed, what you find is that the bootstrap predicts that the coupling constants have a variance. It turns out that that answer is a beautiful interpretation in gravity. It's literally the Einstein-Hilbert action, gravitational action of some wormhole. Okay? In particular, here I've sort of sketched the wormhole for you here. It's got one boundary over here, one boundary over here, and I have 3 points here. Those are the three operators OI. So it's got 3-point function of those operators OI over here, a 3-point function over here, and it's computing the variance of those coupling constants. So not only does the conformal bootstrap know about black holes, it knows about wormholes as well. Okay? And hidden within the consistency conditions of the conformal field theory are things like the Einstein-Hilbert action, gravitational action, and semi-classical general relativity. Okay. So statistical properties of conformal field theories know general relativity. And in particular, there's a sense in which I think general relativity should be regarded as some universal piece of the statistical property of the space of conformal field theories. Okay. So let me try and say in a little bit more detail how I think we should interpret this. Yes?
Why did you have to write on the previous two slides on a torus and on a higher genus surface?
Because, well, those were comments to sort of mollify the experts in the audience, who may or may not be mollified. I can't see the expressions on their faces.
We wanted to hear about modular invariance.
This is conformal invariance on the torus is modular invariance. So it's invariance under large, okay, fine. It's invariance under large conformal transformations on a torus, known as modular invariance. This is a higher genus version of modular invariance, okay? Didn't want to dive into too many technicalities, so I just said conformal invariance with a parenthetical to either amuse or frustrate the experts in the audience. Thank you. Did I answer your question? Sort of. I can tell you all the details of this, because
I thought there would be like a fun, intuitive explanation.
I could draw pictures. There are a couple of different ways of thinking about it. You want me to draw pictures? I have 10 minutes left. I'll draw a picture afterwards. Okay. I only have a couple slides, so I'll draw a picture at the end if I have time. Good. Okay. So what does this all mean? What this means is that general relativity, this theory of gravity in ADS3, Einstein gravity in this geometry, is a solution of the conformal bootstrap, but with random couplings. So what does this mean? I showed you this sort of fun slide earlier where I had a list of theories of gravity, a list of corresponding conformal field theories. Okay? And then I have this coupling constant here. What is this? This is the size of the box, or the ADS radius in Planck units. So this thing here is 1 over h bar. Okay? Well, all of these examples up here, these are not semi-classical theories of gravity. These are very, very, very quantum theories of gravity. The size of the box is Planck scale. Okay, so that's nothing like the universe that we live in. Things that are closer to the universe that we live in are things down here, where the number of degrees of freedom is large, h bar is small. Okay. But you notice that I don't have general relativity on the list down here. I don't have semi-classical general relativity on the list down here. Okay? So where does semi-classical general relativity live on this list? Point is that semi-classical general relativity is not dual to an individual conformal field theory, rather to a ensemble average of many conformal field theories. General relativity is described by a conformal field theory with quenched disorder, in the sense that the data that defines the conformal field theory, like the spectrum of the conformal field theory and the set of coupling constants of that conformal field theory, are random variables. And what do I mean by that? Well, another way of saying that is that if you wanted to compute some observable in general relativity, then you might do some path integral of a sum over geometries like this. And this is not given by the observable in any one conformal field theory, but the average over many conformal field theories, some fixed probability distribution. Okay. So when I talk about the dual of semi-classical general relativity, I shouldn't talk about one conformal field theory, but rather a random conformal field theory. So, we're used very much to talking about random matrix theory. So, for example, going back to Dyson and Wigner and people like that, when they wanted to study very complicated nuclei, they had very, very big Hamiltonians. They were too complicated to study, so they modeled them as random Hamiltonians. And this was really the origin of the physicists' approach to random matrix theory. Okay? So random matrix theory is a theory of random Hamiltonians, where you study the statistical properties of very complicated systems. And here, what we're saying is we're studying a field theory version of that, okay, where we have not just a random matrix, but we're randomizing all of the data that defines a formal field theory. In the case of a CFT, we know exactly what that data is. It's a spectrum and a set of coupling constants. And what is the statistical distribution on this space of data? The statistical distribution is general relativity. Statistical distribution is the action of general relativity of an appropriate solution. Okay. I gave you one version of that here, where the statistical distribution of the coupling constants is the action of a wormhole. So I have a few more comments maybe that I'll make. Maybe I'll skip this in the interest of time. Skip that. Maybe I'll just have one more statement on interpretations, and then I can end even a minute or two early. So I told you that my interpretation of general relativity is that it is dual to a statistical distribution over the space of conformal field theories. And I began this talk by saying that, well, that quantum mechanics and general relativity appear to be incompatible with one another. And what I'm saying now is that the way that they're incompatible is precisely characterized by the statement that general relativity, at least in ADS, is not described by an exact quantum mechanical theory, but by an average over many quantum mechanical theories. A real quantum mechanical theory has fixed coupling constants and a fixed spectrum. Okay? And so a UV complete theory of quantum gravity, an actual quantum theory of gravity, something like what a string theory in ADS might look like, is not an ensemble. It's a normal quantum mechanical theory. The point is that they can look a lot like a theory with random coupling constants. So you imagine starting with some theory of quantum gravity that's an exact quantum mechanical theory, and then you just look at the statistical properties of the theory at high energy. You look at things like the density of states at high energy. You look at the statistics of the coupling constants at high energy. And that's something that we do all the time in statistical mechanics. It's what we call coarse graining. Okay? And the point is that that coarse-grained theory is exactly captured by general relativity. Okay? But in general relativity, you just treat those couplings as actual random variables, rather than things that emerge from some coarse graining. Okay? So the conclusion is that general relativity is the theory of coarse observables, in the sense of coarse graining from statistical mechanics. This is really supposed to remind you of the disorder average theory of a spin glass. Right? So, for example, if I have a chunk of material, right, that's some spin glass, it has an actual Hamiltonian with actual energy levels and coupling constants that are just some numbers. The point is those things are very, very complicated and very hard to describe. So to come up with something easy to describe, we treat them as random variables and study the theory where they're actually random variables. And that's a theory that works very well for some things, for computing properties of the densities of states and things like that. And it works very poorly for other things. Like, you don't get the exact microscopic structure of the theory at very, very small scales. I think what we've learned is that general relativity is just like that, okay? It is the analog of the disorder average theory of the spin glass. And exact string theories and stuff like that are the analogs of the individual quantum mechanical systems that might be, the actual chunk of material, right? But the point and the reason why all of this makes sense is that in most cases, when you have a chaotic theory, this averaging procedure is essentially harmless. Okay? Most systems, indeed any system that's not integrable in a strict sense, will have the property that it's self-averaging. In the sense that as long as you're only focusing on sufficiently coarse observables, then treating very complicated coupling constants as random variables is essentially harmless. Good. Okay, I had one more aside on an aside, which I think I'll skip unless some experts are interested, and just end with a bit of rampant speculation. Okay. So today I described a very restricted class of theories, these two-dimensional conformal field theories, three-dimensional theories of gravity. One common complaint I get is that three-dimensional theories, three-dimensional general relativity is vastly simpler than four-dimensional general relativity or other theories of gravity. Paul, I was sort of expecting you were going to complain about that, but I guess
Not allowed.
you're not allowed. Excellent. So what we've seen is that for a very simple theory of gravity and a simple class of conformal field theories, we can understand general relativity as a disorder averaged theory. And so I think the conjecture that one would make then is that this is true more generally, and that general relativity in anti-de Sitter space should be dual to some probability distribution over the space of solutions of the conformal bootstrap. What probability distribution should it be? Well, I think there's only one probability distribution that anyone should ever talk about, which is a maximum entropy probability distribution. So the conjecture would be that general relativity is the maximum entropy probability distribution over the space of solutions of this very interesting and hard conformal bootstrap problem. And we've seen this in one case, but for other more exciting theories, that's still an open problem. I'll end there. Thank you.
I think we have time for questions. Yeah.
Great. So lots of background with holographic duals, and I enjoyed the insight that they gave us into quantum systems with really specific predictions and things we could measure at CERN and cold Fermi gases and whatnot. Many years ago at Aspen, it was suggested that it might go the other way. That some of the quantum solutions in maybe a CFT or other holographic duals would help us understand gravity better, and I think that's what you were arguing.
Exactly. Yeah.
I don't see any new predictions, number one. And so I'd like to know if you have any in mind. And the second thing is, you kept mentioning semi-classical, but for us in quantum, the interest in black holes has been, beyond semi-classical, beyond Hawking, information scramble.
Yeah, I mean, okay. Many of the statements that I made were true in some sort of strict large, semi-classical limit. But, don't have to take that strict limit. Like if you look, 24 is a pretty big number, but it's not infinity. Okay. And so, there are a lot of statements. And so what that means is that this is a particular conformal field theory. It's a theory of 24 chiral bosons on some lattice. And, there's a sense in which the states in that theory are dual black holes. Okay. Similarly, as we discussed earlier in an answer to a previous question, when people study the SYK model, that's a quantum mechanical model. You study it at finite n. I don't remember exactly what n they were studying it at. Order 10 with a very loose definition of order. Maybe it was 8, maybe it was 16. I don't remember. But in that case, the gravitational theory is a pretty good description. Semi-classical approximations be pretty accurate, even at relatively, semi-classical descriptions can be pretty accurate even if you're not strictly at h bar goes to 0. Okay, so I think there's lots of things we could say. As to your first question about actual predictions, I think I want to be a little cautious here because the theory of gravity that I'm studying is not, this is not, first of all, we don't live in anti-de Sitter space, as far as I know. Second of all, we don't live in 3 space-time dimensions, as far as I know. I think I would have noticed. I think we live in at least 4 space-time dimensions. So, I'm not going to have any super direct predictions just based on this class of models that I'm talking about today. I really think of these as toy models that we can use to kind of probe our understanding rather than ones where I'm really going to try and, make any like hardcore experimental prediction. Right? And I want to be straightforward about that. Yeah.
Thank you. I enjoyed your talk very much.
Thank you.
So, what can one say, maybe this is beyond what the specific problem you have addressed here, what can one say about the toy model of just QED in ADS3, where space-time structure is as you're discussing here?
Okay.
Can one say anything about, the structure of how material is distributed, how radiation is distributed? Any general statements, if not,
Good. I mean, say a few vague things. Okay. But what I described here is general relativity without matter. Okay. I could certainly put matter in. I could certainly put
charge matter.
Charge matter. I could certainly put lots of other things in. Then we would have to modify this conjecture somewhat. But I think that the way that you would modify it is quite clear. Instead of computing the maximum entropy probability distribution, I would compute the maximum entropy probability distribution subject to some constraints, which is what we always do. You put in existence, some additional, whatever symmetries you have, whatever fields you have, you specify correlation functions, then you compute the maximum entropy probability distribution subject to those constraints. You get what's called a generalized Gibbs distribution, okay, if those words are interesting. And so I think the general story is here. Whether I can say anything that'll make you particularly excited about QED3 and ADS3, I don't know, but I think that's the general strategy that I would advocate. Yeah.
Okay. Yes. Now you can ask a question.
About this conjecture.
I mean, it has very strong implications. That.
Yeah. So, why is it that you say that conformal symmetry is realized by the individual quantum system as opposed to, let's say, emergence when you actually after doing that?
I'm not quite sure what you mean. I'm averaging over the space of conformal field theories, each of which has conformal symmetry.
But why should that be the answer to this? The answer to the gravitational path integral, as opposed to, could it be that the gravitational path integral is actually computing not an average of CFTs, but average quantum systems that are individually non-conformally invariant, but only.
It's certainly possible that general relativity is an average over something more general than conformal field theories. Like, I don't know, actually in the paper where we did this, we're sort of circumspect and we said it's an average over CFT data rather than CFTs. The reason is that solving the conformal bootstrap is hard, so we could only approximately solve it, and so we only, there's a story there. So, I think at the level of detail at which we're able to do computations, because we can't actually characterize the full space of conformal field theories, I can't tell the difference between general relativity as an average over conformal field theories or an average over data that is very close to being a conformal field theory. That's a fair point, yeah.
Oh, So, I may be confused, but without constraints, isn't the maximum probability distribution, maximum entropy distribution, just the equal probability distribution?
There are constraints. So for example, these are bootstrap constraints, right? So this is a constraint, right? This is a constraint, right? So this, so for example, the maximum probability distribution over a continuous variable with zero mean and fixed variance is Gaussian. Okay, and so that's the statement that and indeed the action of this wormhole is a Gaussian, is computing that variance for you.
You have a question? Yes. A very stupid one, but I hope you will bear with me. So you made a claim about conformal filters being very relevant because renormalization takes you there at a fixed point. I always wondered, why do they have to converge to a fixed point? Why can't they be limit cycles? Why can't they?
I mean, there are people who do talk about limit cycles in renormalization group flow. I mean, it's a rather subtle thing. Like, as far as I understand, there aren't limit cycles of renormalization group flows. But there's some controversial statements in the literature, but I think the consensus is probably that there aren't limit cycles.
That example,
Yeah, are things that people call...
In 2 and 4 dimensions, there is a quantity that is decreasing monotonically.
Exactly.
Normalization group flow, right?
Yeah. Exactly.
So you can't have limit cycle.
There are things that people call limit cycles, but I don't think they're what you mean by limit cycles, where one coupling can cycle, but other couplings flow monotonically. Yeah. But as Hiroshi said, there are quantities that are monotonic. So for example, this thing that I called C, you can actually define it for all field theories in 2 dimensions, not just for conformal field theories, and you can show that it decreases monotonically under a normalization group flow, which would rule out limit cycles.
Okay, so last question.
This is a dumb question, but so you have your box made out of geometry, right? I see how the black hole would be in equilibrium with radiation when it's reflected back at a boundary, but I don't see what happens to the radiation as it moves out in space.
Yeah, so, good. That's a great question. This picture is a pretty good picture of anti-de Sitter space, but it's not a perfect picture of anti-de Sitter space. A better picture of anti-de Sitter space is, it's a box made of geometry, but geometry is gravity, okay? So anti-de Sitter space is a gravitational potential that looks like this, okay? So this is your distance, and this is the gravitational potential. And it has reflecting boundary conditions for the very simple reason that if I'm here and I send something out large radius, it'll roll up the side of this potential and then it'll roll back down. Okay? So the reflecting boundary conditions are built into the geometry of anti-de Sitter space. That's not captured by this picture. So that's the flaw of this picture. So anti-de Sitter space contains within it the rule that everything will come back. It has reflecting boundary conditions. Great question. Thank you.
Okay, I think it's a good time to stop. We have wine behind this, so thank you very much.
Thank you.